Alright, what's going on, you guys? Another LeetCode video today. This problem is called letter combinations of a phone number. So we're given a string containing digits from 2 to 9 inclusive. They want us to return all possible letter combinations that the number could represent. And the answer can be in any order. Um, so basically, we're going to have a string called digits, and it's going to have only digits between 2 and 9. And then basically what they want us to do is just generate a vector of strings of all of the possible letter mappings that this number sequence could map to. So we can see, we have AD, so the 2 can map to either A, B, or C, and the 3 can map to either D, E, or F. So we basically got to just put all of those combinations into the result vector. So, one combination is AD. Those are the first 2 possible letters from these 2 mappings respectively. AE, basically E is just, the next possible available letter in 3, so on and so forth. So yeah, let's just get into the whiteboarding. So the way we're going to solve this problem is with recursive backtracking. So also, we're just going to use a map, and I've already gone ahead and outlined what our map is going to look like. We're going to have a literal hash map, or a unordered map in C++ for constant get operation. But we're gonna map, basically the string, or the char really for 2, 3, 4, 5, etc. to 9 to the corresponding. It's just gonna be a string containing all of those letters, and we'll hard code that in. So that's how we're gonna handle the mapping. But as far as the recursive backtracking goes, let's get into the specifics for that algorithm. So we're gonna let's just look at the string that they gave us in that problem example. So they just gave us 2, 3. So let's try this on that string. So we have 2, 3 here. We're gonna have, so let's say we seed our recursion here. We're gonna have an index that basically just tells us which element we're at in the input string they gave us. So first we'll start at the 0. So we're also going to have a string for the current mapping, and at first that'll just be empty. So let's go ahead and get into that first call. So, and there's gonna be quite a few of these actually, so let me spread out here. So we're gonna go ahead and increment that I by 1, right? So I is gonna be 1. Okay, but this 0 here indicates, what index or what element we're looking at based on its index in the input string, right? So we're looking at the 2, and basically that's gonna tell us, okay, we're gonna use our hash map, and we basically just want to do recursion and then backtrack for every single one of those letters that we can map this 2 to. So, the first thing we'll do is, and I'll just do this in a different color, that way I don't have to keep writing quotations over and over again. This is going to be a string, right? So we're first going to add that A, and then, in the next, at this same level, the we would backtrack, right? So we'd remove that A from the string, right? We're still going to be at 1 here because, we're still at this, we want to, basically this 1 is going to indicate, okay, for the next calls, that's the index we want to be looking at, right? So anyways, we're going to backtrack that A, and then add the next available letter, which is B. And then same thing, we're going to, for this call, we're going to backtrack that B, and then add the next available letter, which is in the map, which is C. And that's going to be it for the first level of our recursive tree, right? So now we're going to go several different ways for each of these, right? So that 1's going to get incremented, right? So to 2. So basically what that means is now we're looking at the next, we're going to be looking at this 1, right? But that's going to tell us for potentially the next iteration, and there won't be another iteration after this because 2 is the same. We're basically going to be doing our recursion until, that index is equal to the size of the input string, because then we know we've done every single character in that string. But anyways, yeah, we're going to add, so we have the A, and then what's the first available candidate for 3? I forgot to do this, so we're at the 3. So it's going to be D. All right, and by the way, this is going to be part of our answer, so let's go ahead and I'll just underline that to show that. So that's part of our answer. Here we have 2 again, same thing, but we're backtracking that D, right? So we have the A, and then we backtrack. What's the next available candidate? It's going to be the E, right? So we've got that. The size there is equal to the size of the input, so that's part of our solution. So we're going to push that to our result vector. Same thing. We backtrack, add the next available, which is F. All right, and that's going to be it for this part of the tree. So, so going back to the same level, or the previous level up here. So we're going to have a 2, we're going to bring down that B, and then basically do the same thing, right? So we tried a D first, add that to the solution. So I can actually, I do want this to be complete, but if I keep doing it in order like this, it might take an entire lifetime. So let me just finish the tree out of order really quickly, and then we'll discuss this more. So right, so all of these indices in each path basically just ends at 2, right? We're just building these strings until they have the correct length. So this is BE, and then BF after the backtracking. So we have CD, we backtrack, and we have CE, backtrack, and then we have CF, right? And then that's all of our combinations. So, and then part of the reason why I wanted to finish this tree is just to show the time complexity, right? So it helps show the time complexity. So yes, for the time complexity for this problem, we're gonna have to basically build a bunch of strings, right? Okay, but how many strings? Well, notice how many notice how many options we have at each branch in our recursion, and also notice how it's not decreasing. It's pretty much a uniformly consistent number of choices to make, right? So whenever we have something like that, the time complexity is usually whatever the branching factor is. The branching factor here is going to be 3, and then how many times, right, do we have to make 3 choices? Well, it's going to be n times, if we say n as the length of this input string, so 3 to the n. And it could be 3 to the n, but some of these mappings actually have 4 different choices, right? So being that big O is a worst case notation, we have to say that this is big O of 4 to the n for the time complexity. So that's how long it's going to take. For the recursion, for the space complexity, it's just going to be big O of n for the space required by the recursive stack. Because the recursive stack is proportional to the height of the tree is going to be of height n, right? So we could just say big O of n for the space complexity. There's also some space for this hash map, but that's just constant, right? Not going to change regardless of the test case. The hash map is never going to We're never going to add or remove anything from it. It's just a part of the code that's constant, right? So that's the time and space complexity. So let's just get into the solution here. So for letter combinations, let's see. So the first thing we're going to want to do is just have a vector of strings for the output. And we'll just call that res. We're also going to want, let's see, we're going to want to build that hash map. But before we even do that, let's actually check for the edge case where digits is empty. So if digits dot length is 0, because we don't want to have to actually build the hash map if there's nothing, if digits is empty, right? And it can be, I'm pretty sure. Yeah, so digits length can be equal to 0. So just to make a little bit of an optimization, we can just go ahead and return res in its empty state if there's nothing in digits. Okay, otherwise, we're gonna have to initialize that unordered map. So we'll take char values for the key, those will be the digits, and then the letters will just be in the form of a string. So, and we'll just call it map. So now let's set each of these values. So actually, instead of you watching me type that a million times, I can actually just, let me pull this in from my other screen here. So this is basically just hard coding in all of those key values for the map, right? So just saving a little bit of time there, so you don't have to watch me type all of those. Yeah, so we're gonna want to have some recursion, and I'll use the same function. I'll just overload the same function for our recursion. So we're gonna do letter combinations, and we need to write that function signature. Not too sure what the parameters will be yet, but we'll figure it out. And then we're just returning result after that. So we're gonna have the letter combinations recursive function overload over here. It'll be a void function in the sense that it doesn't have any return value. So void letter combination, and then let's figure out those parameters. So we're gonna want an integer to tell us where we're at in the input string. We also want a string, just the one that we're currently building. So I'll just call that S. And in addition to that, we're gonna need the digits. So that can just be by reference. So just take a string digits for the input string. We also want the vector of strings for our final result. And then we want that unordered map, right? And it's an unordered map of, we're running out of room here, so let me make this bigger. So it's an unordered map of char keys and then string values. And that'll of course be by reference. So we're not copying it in each recursive call, right? That would get very expensive. So definitely want that by reference. So the first thing we do here, so for the base case, is to check if the string is finished. So once I is equal to digits dot length, and actually an even more robust way to check that, we could also do s dot length, right, to ensure this literal, the string itself, and that should be constant time operation, is the same as digits dot length, right? Because that's what we're looking for when we add the completed mapping, right? So we'll say to the result vector. So result, I'd push back S, right? That's a completed mapping for the string S. And then at that point, we just return from this path in the recursion. If we're not yet returning, then we need to keep building the map string mapping, right? So first, let's go ahead and get those characters that are our options, right? So we'll just say string options is going to be equal to the map for the character at digits I, right? right? So that'll get all of the options for the character we're at in the string digits. Okay, and then we just want to loop through those options. So for auto character by reference in options, in those options, we want to do basically first want to try that option by adding it to the string. So we'll say s dot push back. We can and since it's a string, we should also be able to do plus equals, but I'll just use this pushback notation or syntax because I've done a lot of other problems with backtracking this way. So just to keep things kind of consistent in my brain. So s.pushback c, then we want to do the recursion, so letter combination for I plus 1, and then that string s, right? Digits is going to always stay the same, so is res, and so is map. I mean, we're going to be adding to res as we finish the mappings, but we can keep passing it through the same way. So after that, we've got to backtrack, right? So we're going to do s.popback on the option we just added for the next iteration, so we can try the the other options, right? So that's pretty much it for the code. Do have to seed this recursion here. Definitely don't want to forget that. So 0, it's going to be the index at first, empty string at first, and then digits, res, and map. All right, so that should be it now. So let's go ahead and run this. See if there's any bugs. There are, so too many arguments. Let's see. Letter combinations, because I didn't overload this properly, or gave it the wrong name. So that should be the only bug there. So let's see. Oops, one more. All right, and there we go. So hopefully this video helps you understand letter combinations of a phone number. Sorry, I forgot what the name of the problem was. But anyways, yeah, hopefully this video helps you understand that problem better. If it does, leave a like and subscribe. I'll see you guys in the next video. Peace.